Good evening, everyone. My name is Tinggao. I'm from Applied Math. My topic for today is social networks with application in viral marketing. First, let me introduce the outline for today. First, I'll talk about the motivation of my topic. Then, I'll move on to how to build probability model for marketing with social network knowledge. And then I'll talk about how to mine some useful probability data that is needed in our model. And the next, two real data examples and their corresponding results will be shown. Finally, I will summarize the conclusions. First, let me begin from the motivation part. There are a lot of marketing strategies, for example, mass marketing. The basic idea is to ignore population segment difference and broadcast a message that will reach as large number of people as possible. Another one is direct marketing, which is based solely on customers' characteristics or historic behavior by using cell phone message or email or online ads, etc. While nowadays a growing number of companies begin to use so-called viral marketing. They use pre-existing social network and other statistics techniques to increase product sales or brand awareness through self-replicating viral process like the spread of an epidemic. Compared with the above two marketing methods, viral marketing is much more cost-effective, since viral marketing takes the advantage by making primarily to those few people who have strongest influence in the market. Therefore, our motivation is now to build marketing model from social network to help companies determine which potential customers to market to so that they could gain more profit with less expenses. So how to find the optimal marketing plan? The basic idea is, given some real data, first, mine some social network structure from this data and gain some useful probability data that are needed in our model. Then plugging this probability data into our marketing model and try to solve an optimization problem so that the best viral marketing plan can be obtained by maximizing the total profit. In the following, I will mainly focus on these two papers, which use social network to improve marketing plans in real world. So without ignoring the network effects, we should not only consider a customer's intrinsic value, but also his network value. Therefore, the customer's value is defined as his intrinsic value plus the network value. The intrinsic value is defined as the expected profit from sales to the customer, while the network value means expected profit from sales to other customers that this customer may influence too. Here is a real data picture on the customer's different network value. We can see that the red dots all have high network value since they can influence a lot of other people. However, the blue dots, such as the one in the red circle I marked here, has very low network value. Now, let's move on to the model. First, let me introduce some notations. Here, xi represents the customer I. It's a Boolean variable, could be 0 or 1, represents whether customer I will buy the product. And here Ni denotes all the neighbors of customer I. And since in this model, they assume the probability of whether customer I buys the product depends on these three variables: xk, which represents customers whose value is known, and y, the product attributes, and m, marketing action. Therefore, we will need to compute the probability of xi given xk, y, and m. In another paper, since the purpose of this paper is to calculate the optimal marketing plan for a product that has not been introduced to the market, In this situation, the state of the neighbors will not be known. So, we only compute probability of xi given y and m instead of probability of xi given ni, y, and m. So with these probabilities in hand, we can define the global lift in profit now. So the ELP here represents the expected lift in profit. It is defined as the total revenue after marketing action, which I marked using the red circle here, minus total revenue with no marketing action, which I marked using the blue circle here, and minus total marketing cost. Note that here R1 is defined as the revenue from customer I buying the product if marketing action is performed to him, while R0 represents the revenue of selling the product to customer I if no marketing action is performed to him. The difference in the second paper is that in the second paper, the R is now a continuous function defined on interval 0 to 1. And the cost C is also a continuous function instead of a constant. Therefore, now we have an optimization problem. That is to find the marketing action that can maximize the expected lift in profit. In 2001's paper, for the Boolean case, for each customer I, mi can only be 0 or 1. So 0 means not do marketing to customer I, and mi equals to 1 means do marketing to customer I. And here small n is the total number of nodes or customers in the social network. In 2002's paper, for the continuous marketing case, mi could be a variable between 0 to 1. We can think this indicate different discount that is offered to different customers when doing marketing action. So how to solve this problem? For Boolean case, we have mainly three searching methods: single pass method, greedy search, and hill climbing search. And for continuous case, assuming that for each customer I, the expected lift in profit is twice differentiable with respect to marketing action mi, which is now replaced by z here. So we only need to solve this equation and check the second derivative to be smaller than 1 so that the maximum value is obtained. Note that now we only need to know these two probabilities that were used to define the expected lift in profit in the above slides. So now, how to get the two probabilities? For the 2001 paper, from total probability model, we could get the probability P of xi given xk ym intuitively if we know the probability P xi given ni and y and m. And also by Bayes' formula, if we know these four probabilities, we could get the probability of P of xi given NIYM. Among these four probabilities, all of them can be obtained through the counting method by real data, well, except the probability P of xi given Ni. So the problem now is how to find this probability P of xi given Ni. Where in 2002's paper, recall that we can model the probability of whether customer I by the product given y and mi equals to two elements the summary of customer I's internal probability of buying the product, and the second term, the effect of the neighbors on customer I of whether to buy the product. Here, the beta I is self-reliant parameter, just the weighted parameter for these two elements, and omega ij is the influence of j to I to customer j to customer I. The interesting thing is that this is more or less like the PageRank algorithm used by Google to determine the important web pages. In PageRank, a web page is valued highly if many highly valued pages point to it. Similarly, in viral marketing, a customer is valued highly if he influences many highly valued customers. In this formula, we can see that if the probability P0 of xi given ynmi is known, then we could get the probability P of xi given ym iteratively. Therefore, now we need to find the probability P of xi given ni and P0 of xi given y and mi from our real data. In fact, these two probabilities differ from case to case. Therefore, the author chose the collaborative filtering database and knowledge sharing sets for these two cases respectively. A well-known standard dataset for collaborative filtering database is the H-movie dataset. They collected millions of ratings of thousands of movies by 10,000 of users, and here xi denotes whether the person I saw the movie. For the movie that the customer didn't see or didn't rate, a predicted rating will be calculated for him from a weighted average of his neighbors. Here the neighbors means those people who have similar movie favorites of this customer. In this way, we can think that the probability of xi given ni equals to the probability of xi given the predicted rating of customer I. In this way, all of the probability data that we needed in the model could be get. And for the opinion case, the opinion dataset is also a representative for the knowledge sharing sets. In opinion, members submit product reviews and users interact each other by rating reviews and also listing the reviews that they trust. Therefore, a network of trust relationship between the users will then be built, and it is called the web of trust. In this case, the xi denotes whether the user I bought or reviewed the product, and ni means the users trusted by customer I. Then by naive Bayes formula, if we know the probability P0 xi given y and P0 mi given xi, then the probability of P0 xi given y mi could be obtained. And these two probabilities, P0 xi given y and P0 mi given xi, could be easily obtained by counting method from the real data. So now let's see some examples in detail. For each movie, to get all the probability data, the author used piecewise linear model to interpolate linearly between two nearest means calculated from each of the 9 bins. We can see this in detail from this following picture. This picture is the empirical distribution of the predicted rating and the conditional probability of whether customer I saw the movie given his or her predicted rating. Note that here, the predicted rating Ri hat is forced to be centered at 0. for convenience, which means it has been subtracted of customer S average rating. We can see that the distribution of the predicted rating Ri hat obeys kind of like the Gaussian rule, while conditional probability of xi given Ri hat is more interesting. This shows that if the predicted rating is far away from his or her average rating, then this also means his neighbors like or dislike the movie very much. Then the probability of the customer I saw the movie is much higher and closer to 1. Here I marked it using 2 red circles. However, the probability of those movies with similar ratings to customers' average rating may have been seen very unlikely. That's in the red middle circle here. So, and also furthermore in the small interval minus 0.1 to 0.1, where the highest density of ratings is, the conditional probability is indeed monotonically increasing, which is also what we have expected. Here is a result from both each movie and opinions. Both of them show the typical distributions of network values. For example, let's see the left figure. It shows 500 highest network values in decreasing order. The network value of 20, for example, for a given customer implies that by marketing to this customer, we can get free marketing to an additional 20 customers. Note that here, the customer's network value equals to the total value minus intrinsic value. Here is the most essential result from each movie. These figures compares 3 searching methods on both viral marketing and direct marketing for 3 scenarios, which are free movie, ads movie, and discounted movie. For 3 movie, R1 equals to 0. Note that here R1 we have mentioned before, meaning the revenue from selling the product to customer I if marketing action is performed to him. While advertising means we can get the highest revenue, so R1 equals to 1. And discounted movie is R1 equals to 0.5. Here, note that viral marketing means performing marketing action when total value larger than 0, while direct marketing means only intrinsic value larger than 0. We can see that no matter which of the 3 search methods are used, viral marketing always gets more profit than direct marketing. And among all these 3 methods, hill climbing search is much more time consuming, especially as alpha increases. This can be seen from the lower right figure. So here are some results from opinions. Here is some different profit results of continuous marketing for 3 cases. That's no marketing, direct marketing, and viral marketing. The first 3 lines shows the continuous marketing action. We can see that no matter how much budget we choose, which means we chose different value of C, viral marketing always has a larger profit than direct marketing. And direct marketing always has larger profit than the no marketing case. The last line is Boolean case for viral marketing, which also calculated by the opinion by the 2002 paper. We can see that the viral marketing for viral marketing continuous action performs much better than Boolean case. For example, when C equals to 0.1, the continuous case has 41 percentage more profit than Boolean case. Here is another result from e-pinning. One limitation of the 2001 paper is that they require full knowledge of the network structure. However, in this 2002 paper, this limitation is overcome. Here is a picture on the difference between viral marketing and the direct marketing profits with only partial knowledge known. We can see that even the fraction of edges known is very small. The viral marketing always get more profit than direct marketing. And furthermore, the algorithm considerably underestimates the lift in profit in active marketing case, which is much better than what we have expected. So now let me summarize the conclusion that we can get. In both papers, they view customers or users as the nodes of social network, and the edges are constructed by the nodes similarity or trust relationship. And both of the papers use data mining techniques to get the probability data that they needed so that they improve the viral marketing action. And the difference of the two papers is that first, model the the 2001 paper used nonlinear model to model the neighbors effect. However, 2002 paper used linear model. Therefore, in 2001 paper, they can only deal with the Boolean marketing actions and require full knowledge of the network structure. However, in 2002 paper, this limitation were overcome and continuously variable marketing actions were addressed, and also they deal with partially network knowledge. Thank you for your attention.